Okay, good afternoon, everyone. My name's Kate, and I'm a Business Development Manager in the CPD unit at Cardiff University. I'm really delighted to welcome you all to this session today, and thanks so much for joining us. We're going to take questions towards the end of the session, but there's going to be a bit of interaction and discussion throughout, I think. So all it requires now is for me to, really pleased for me to introduce Dr Vicki Stevenson, who's going to be taking today's session. So thanks very much, Vicki.
Sorry, thank you very much, Kate. I made the typical mistake there of still having mute on. I'm just trying to find my share screen button. And there we go. Kate, can you just let me know if that's showing up okay?
Yeah, that looks fine, Vicki.
Great. Well, thank you to everybody that's joined us. I know you could be having your lunch instead, so it's really great that you're interested in this. I'm Vicki Stevenson at the Welsh School of Architecture at Cardiff University, and we're going to have a quick run through some facts relating to ventilation and air quality, and that's related to the Environmental Design of Buildings MSc, which I run. So apologies if we don't cover everything that is of interest to you. It's quite a wide topic. I'm trying to pick up some of the major points. So first of all, why do we need ventilation? And one of the most important factors here is improving our air quality. We always need to get fresh oxygen into the building, and at the same time we also need to remove pollutants. We also need to remove internal heat gains. That's the heat that's generated by us as humans and by the appliances and lighting that we use. And in hot climates, and I've got to say today, South Wales is feeling like a hot climate, comfort ventilation can be really useful. What we get there is just the air movement over our skin, just basically evaporates the moisture on our skin and cools us down. The airspeed is quite important on that. The higher the airspeed, then the more cooling we get. And also the fact that we wear clothing which allows that air movement to get in contact with our skin. So I mentioned about the airspeed. If we're sitting down, then you can only tolerate a fairly low airspeed. But as we get more active, particularly if the gentleman there that's cycling or in the dance studio, we can tolerate much higher airspeeds, and in fact we welcome them for that cooling purpose. So now we understand why we want the ventilation. Let's have a look at a few of the ways where we can actually bring that ventilation into our space. First thing I'm going to look at is openings. Now those could be purpose-made vents, but in the UK, and actually in several other countries, we tend to treat our windows as also our ventilation option. Then I'm going to look at a couple of other options that might be useful where openings aren't so suitable. So there'll be the wind catcher and the solar chimney, which utilises the stack effect. Don't worry if you don't know what that means, we'll get to that in a little while. So first of all, looking at these openings for ventilation, and I just want to be clear about two terms that you might hear in relation to this. So ventilation is controlled. If you open up a window, you get some ventilation, you close the window, it stops. Whereas in a building, quite often we have lots of cracks that we don't really know about, maybe around pipes that bring the services in. And in these little gaps, we get air movement coming in. And that's infiltration, that's uncontrolled because we can't switch it off. So while we're looking at our windows as a type of opening, it's important to understand what different types of windows can afford us in terms of ventilation. So we have a fixed window, we can't open it, so we're not going to get any air through it. We have an awning window. Now this shows as a top hinged window in the image, but it could also be a side hinged window. And depending on the wind direction, that counts as a sort of 12 to 30% opening in relation to the wind direction. A sliding window, we can normally get about 40% of that opening available. And a louver window, we can get up to 90% of an opening in the space. So that's just to give you some ideas of what types of openings we might have if we're using windows. Of course, getting the ventilation isn't the only important thing. We need to be very careful about security. We don't want anybody falling out of a window, and we don't want unwanted visitors coming in the windows. So we also want to know, can we properly close that window so that we're controlling our ventilation and not having infiltration? That's one of the disadvantages of louver windows quite often, because they tend to be bare glass to bare glass. Although they open well, we don't always get a good seal on them when we try and shut them. So next thing to consider are number of openings. Don't worry too much about the graph. It's really just to show in this case that when we have multiple openings, we can get much higher indoor airspeed than we would if we just had a single opening, even if we've got a really big single opening. And then if we have these openings, how do we consider those in relation to the wind direction? Now, the image I have in the top right-hand corner is a windrose, and it's showing quite an unusual wind pattern. It's showing a very directional wind pattern, and that's deliberate because I'm going to do something with that in a minute. But it's important that you know that most wind patterns are much more rounded. There are very few places that have such a wonderfully directional wind direction. So a little quiz for you now, just to make sure nobody's drifted off to sleep while I'm talking. And don't worry if you don't get it right, because we're going to talk about it in a minute. But just intuitively, what angle would you think the opening should be to the wind for the best ventilation? Choice A is normal, so that's the wind coming directly towards the opening. Choice B is 30 degrees away from that, and choice C is 60 degrees away from that. And if you could respond through the chat or the Q&A, that would be really great, and Kate will let me know what your thoughts are.
So far, Vicky, we've got quite a mix of answers actually, quite an even spread of A, B and C. So we're divided.
Well, that's fair enough. So I'm just going to explain a little bit about this. So the first thing we're going to think about is the normal wind. So that's if the wind is coming directly towards the opening. And if you think about that, it's almost like blowing into a balloon. But the advantage of a balloon is it can increase in volume to allow more air in. The room can't increase in volume. So once the room is full of air, you don't actually get any exchange of air. So actually, if we have oblique wind, so that's the 30 to 60 degrees, it can create a pressure gradient along the windward walls, and that allows some air movement, which allows a circulation of the air. Particularly if we've got more than one window, then here we can see if the wind is coming directly towards those openings, it just really sort of fills up the room. There's no circulation to get it back out. So that's why there's a red cross through the bottom window, which you'd hope the air would be coming out of. But if we have that oblique wind towards the windows, the openings, then you get that lovely current through the room, which means that we're getting really good ventilation. We're getting fresh air in and exhausted air back out. So all of you who guessed sort of B's and C's, you were correct. And those of you who guessed A, you had a reason for your logic, and that was an explanation of why B or C would be better. So in terms of our openings, how can we place them and what size should we have? So I think intuitively we'd realise that large openings increase our airflow rate, and equal inlet and outlet tends to maximise the airflow rate. And having an equal inlet and outlet size also protects against changes in the wind direction, which are quite common. We generally find the wind changes direction quite quickly. Now you can have the inlet much larger than the outlet, and that's a really nice, low but uniform air velocity. And if you switch it around, you're going to get a really good high air velocity, which is only really suitable for a high activity room like a dance studio. Now our problem might be if the wind switches direction, then we'd set our inlet to be larger, but suddenly it's the outlet that's larger. And if we're in an office where we're all sitting down, then maybe we're getting this air whooshing through and stirring up all the papers. So the inlet and the outlet being even protects us from that kind of change. So again, another little quiz. If you were placing two openings of the same size, which of these options would give the highest indoor air velocity, where A is on the same wall, B is on adjacent walls, and C is on opposite walls?
So we've got a lot of people opting for C, some B as well. So a mix of B and C really.
Great. So I'm going to give you a little bit more information, then we'll go back to answer that question. So here we've got a grid which shows sort of like the 9 spaces there could be on a wall if it's split into a grid of thirds along the width and along the height. And if we look at those openings, how much the air velocity indoors is going to be as a percentage of the outdoor wind velocity. So if we've only got one opening, so that'd be like that one little window in the middle, then we get about 12 to 14% of the air velocity from outside. If we extend that across the entire wall, we can get up to about 23%. As soon as we start opening 2 openings in that same wall, we're straight up to about 22, 23%. So immediately you've got that benefit from having 2 windows, even if it's in the same wall. When we move on to adjacent walls, we can get between 37 and 51%. And when we get to openings in the opposite walls, we can get between 35 and 65%. So those of you who got to C, absolutely great, because that was the highest velocity we can get through a space. And those of you who were B, you were in the right territory, because we can still get really good airflow by having the wind in adjacent walls. Both of these are far better than having the openings in the same wall, but if you've only got the opportunity of openings in the same wall, it's a real advantage to have 2 openings rather than just one big one. And again, if we're looking at the opening size, then we can see that if we've got bigger openings, then we get that better proportion of airspeed indoors as a proportion of outdoors. And this is just a little visual indication of what happens when the wind's at 45 degrees to the inlet in these different options. So we've got single opening, double opening on the same wall, double opening but adjacent walls, and double opening on opposite walls. Something else to take into consideration is how high up we're going to put these openings. Now this can be a bit problematic, particularly when we're using windows, because windows are also used for other purposes, like for instance, for the view, to make people feel related to the outside space. So, I'm taking it from a ventilation point of view. I realise there are other factors you might have to consider. So if we have really high openings, one of the benefits we can have with those is that hot air tends to rise. So even though we're not getting air movement across our people, so we're not getting comfort ventilation necessarily, what we are doing is taking the hotter air, which has risen to the top of the space, and we're blowing that hot air out, but we're not necessarily getting some nice fresh air at people level. If we have low openings, then that's really great for getting the air mixing around the people, so we're getting good fresh air in amongst our people. But also we have to be very careful about the air velocity. If you've got high air velocity and it's going at a low level, people tend to get cold feet and ankles, so you can get a lot of comfort complaints. And you can also have variations between the high and the low openings to try and mix the air and give the best situation you can for the people in the space. Now, as I mentioned about the low openings, they can be a bit of a draft. If you've got a high activity space, then that's probably going to be okay. But if you've got people who are sitting still and unable to move away from the draft, that's when it can be a problem. So just in terms of thinking about this in relation to a real life space, here it's an apartment, then if we're trying to get good ventilation, we want to minimize the obstructions between the inlet and the outlet. So sometimes there might be doors between the inlet and the outlet. We want to keep them open. Even fly screens can reduce the air velocity a bit. And we want as straight a line as possible for the air to flow. Any twists and turns that we give for the air, then we're probably going to reduce its velocity. Something I'm going to speak about now is wing walls, which don't tend to get used very much, but can be really effective. And the whole thing about a wing wall is it's really a protrusion near the opening, which helps guide the air into the openings. So here we can see the air is coming from one part of one sort of side of the room, and the wing wall helps direct it into the space and give it a nice flow around the space. And this graph just shows the difference that can make to the wind velocity in the space. So the bottom dashed line is just a typical opening, and then the solid line above it is that same opening, but with the wing walls built in. So you can see that loads of different wind directions, we're getting a really improved air movement in the space. And I'm not going to go through this in detail because we don't really have that much time, and I would like you to stay awake. But if you want to maybe look at this recording later on or take a quick screen grab of it, you'll see the various ways that a wing wall can be used in conjunction with various openings. And the protrusion should be at least a half to the same width as the opening. So let's have a look at some of these examples in buildings. So this is an example from Jamaica. You can practically see through the building, even from ground level. So we can see it's really built for ventilation to allow that air to go straight across the building, remove the internal heat gains, remove the humidity, and to try and keep that indoor temperature as close to outdoor temperature as possible. We didn't want it to get any hotter than outdoor temperature. Here's another example. Here you can see all the circulation spaces are actually outside the living spaces. So it's only the spaces that actually need privacy that are enclosed. Everything else is open to the air. That means that those living spaces have got opportunity for airflow from lots of different directions. So regardless of where the wind direction is coming from, you've got windows that can open and allow the air to come through. And you can see there's also good overhangs there to protect as much of the building as possible from the heat from the sun. And I actually found it really difficult to find examples of wing walls, despite the fact that they're so effective. So I did find one here on the left, but also it can be possible for some people, if you've got windows that open properly all the way out, then you can use your own window as a wing wall. This is my own house. Please ignore the scaffolding. They were quite late in taking that down, so I had to take the photograph with the scaffolding in the background. But you can see the window is open. The proportions aren't ideal because it was never designed for that. But if I ever have a chance to redesign my windows, I'll be getting that fixed. So that's all the sort of openings that we're going to talk about. Now we're going to look at a couple of other strategies. So here's the wind catcher. And what the wind catcher does is it takes advantage of the fact that the air velocity high up is much stronger than air velocity low down. And the more built up your area is, the more pronounced that is. So if you're in a built up area, then you have to go even higher to get a higher wind speed. And here's an example of this in an old-fashioned city which has been designed. Because it's a very hot city, the buildings are built really close together to help shade each other from the sun. But while they're doing that, they're also blocking each other off from any wind there might be. And the solution there is to build these wind catchers on the roof so that they can capture that air and bring it into their space to ventilate. And this is a little schematic showing how that works. You know, the inside, there's a barrier, so there's an inlet side and an outlet side. And these can be arranged on the building, any orientation, to make sure that they're the best orientation for that local space. And another advantage of this is there's no conflict in this in relation to sun or shade, which there might be if you were using windows. There are four main types of wind catcher. So we're going to have another little quiz here. I'm going to bring back that wind rose that I showed you earlier, which was really directional, with the wind coming mainly from the northwest or the southeast. And I'm showing you four options on wind catcher. One is an Iranian two-sided wind catcher. And you can see the little red arrow there points towards the basically the efficiency of catching the air in relation to the outside available wind. There's a Pakistani one directional, an Egyptian, which is a dominant and a secondary direction, and an Iranian, which is a four-sided one, as opposed to the two-sided one above it. So we've got this wind coming mainly from the northwest and the southeast. If you'd just like to have a guess at which of these wind catchers is going to work best, so would it be A, the Iranian two-sided, B, the Pakistani one-sided, C, the Iranian four-sided, or D, the Egyptian with a dominant and a secondary?
Again, we've got a variety of responses, a number of C's, but we've also got A, B, and D as well.
Great. Well, for those of you who thought C would definitely work. The advantage of a C is that it will work from pretty much any direction. So even if we had a much better distributed wind direction, so a more common wind pattern where the wind could come from any direction, the Iranian one would work. And you can see from the curve there, it's quite a gentle curve. It doesn't go hugely high or hugely low, but it's kind of similar performance, with not too much variance in which direction the wind comes from. I would actually suggest that in this one, an Iranian two-sided would be better because we've got such a strong directionality on the wind. And we can see from the two-sided one that we get a higher performance when it's at the expected directions. But when the wind goes away from that direction, the wind speed can drop all the way down to zero. So there will be times when we're not really getting any air in the space at all. And what we find from these is that the fewer directions that you cater for with the wind catcher, the far stronger air movement you can bring into your space when the wind is in that direction, but we then suffer a much lower, in fact, sometimes even zero wind speed if the wind moves too far away from that direction. And when people are making their designs for this, then it's about designing to match the directional variability of the local winds. So if you've got a much wider variation of the wind, then maybe looking at that four-sided version. And when you're making that decision, there may be periods when you're really interested in having this work, but maybe you don't need it all the year round. So if you only need it for a particular part of time, maybe for the summer months, then you would only have to analyse the wind direction at that particular time. Something else that can be of interest, for instance, if you're in a really hot place and you want a cooling wind, you could focus your wind catcher if there's a local body of water, because that would help cool down and humidify the air that was coming to you. Or perhaps if there's cooler air coming, perhaps over mountains, then you could also focus your wind catcher for that direction. And just so you know that it's not just a really traditional old thing and something that I'm trying to resurrect, there are modern examples of this. So here we've got an example from Qatar University. We've got rooms that are very compact layout, and the wind catchers allowed them to do that. There are also some designs that can swivel, and this is an example from Bedfordshire's zero emissions development. They can swivel to meet the wind, so that can be quite useful. This is the original design from BedZ, which is, in my eyes, very beautiful. They have since simplified the design to make it more efficient and more cost effective, but not quite as beautiful as this one. And there are other examples, like for instance these open stack turbine and deflector options that I've shown at the top there. So now we're going to move on to the stack ventilation, which is also known as a solar chimney. And what we're doing there is trying to facilitate ventilation where the wind is maybe not available at all times. Maybe the building's blocked from the wind by trees or another building. And what we're using is the fact that hot air rises. So when hot air rises and we can have an area that's deliberately exposed to the sun to help that process, we're effectively setting up a current. So the fact that we've got some air that wants to leave the building creates a negative pressure inside the space, which draws in, and if we're very careful about where we put the inlet vent, we can get that from perhaps the cooler side of the building if that's what we're looking to do. Lots of things that influence the airflow. One is the vertical distance between the inlets and the outlets, so it might work better between the ground floor and a high chimney than it will on the top floor and the high chimney of a multi-storey building. There's also the temperature difference between the outside and the temperature in the room, and also the inlet and outlet size. So these are all factors that you would have to look into in a bit more detail if you wanted to use this particular strategy. And again, just to prove that this isn't a figment of my imagination, this is the schematic from the Queen's Building at De Montfort University. Now, ventilation, in my eyes at least, is very closely related to indoor air quality, so I just wanted to do a little bit about that. And some quick facts. Household air pollution is in the top 5 of risk factors globally. Many people spend more than 80% of their time indoors, and I think over the last few months, a lot of us have spent much more than that indoors. In fact, air pollution indoors is often double or even quadruple what we would experience outside. And because we spend so much more time indoors, our exposure to indoor air pollutants can be over 100 times the exposure to outdoor. So let's think about what some of these indoor contaminant sources might be. Well, first of all, there's combustion. If, like me, you've got a gas cooker, then every time you're switching that on to cook, then we're getting gases like carbon dioxide, and if we're very unfortunate, carbon monoxide being released. And the same thing could be said of just something as simple as a candle. Then most of our soft furnishings, they are impregnated with a fire retardant, which is there obviously for safety reasons, but we do have to be aware that this is another source of contamination in the air that we're breathing in. Many plastic items off-gas during their life, and vinyl flooring is effectively a type of plastic. And loads of the chemicals that we use for decorating and maintenance are also releasing volatiles into the air. If we've got a printer or copier at home, and that's becoming very much more common. And in fact, a lot of our personal and cleaning chemicals have got things in them you really wouldn't want to think about. So I mean, all these different things are in our homes and releasing fumes that we're effectively breathing in. In addition to that, there are other things we share our homes with. For instance, we get pollen maybe from the plants that we have around. Humans ourselves, we breathe out carbon dioxide. We have our own bodily emissions, unfortunately, and so do the pets that we might have in the house. And unfortunately, so do the animals in the house that we didn't actually invite in. You know, there's all kinds of little pests and creepy crawlies which are adding their own issues. And also in relation to that, if we get the place damp, we can cause molds and mildews to build up. Thinking about this in terms of the particulates that we might experience. So if we have some coarse particles, they tend not to get too far into our body. We would probably cough, I've got to say, as a hay fever sufferer, a bit of pollen in the air and I'm sneezing uncontrollably. But that's the body's protection mechanism. When you get into the smaller particles, they get further into our lungs until finally, if you get down to the really ultra-fine particles, down to the PM 0.1s, so that's 0.1 of a micron or even less, they're so fine that they really just permeate through our entire body. They almost behave like gases because they've got that ability to get into our entire systems. So what can we do to improve this situation? That's really the important thing. Well, first of all, if we can try and reduce the contaminants in our building, if we can choose materials with low emissions, then that's really helpful. For some people, if they're in an area where there's poor outdoor air quality, perhaps because they're close to busy traffic or something like that, if they have the facility to filter the air coming into the building, that might also be helpful to them. But really the focus here would be trying to get the information, and I have to admit it's not that widely available yet, but I think it's, as people are getting more aware about indoor air quality, this is the kind of information that is going to be more available and people will be able to choose more easily what materials they wish to have in their homes. So that little table at the side, I've highlighted in bold some of the things which are probably the lower emissions if you were going to choose. Now obviously, I'm not trying to impose on anybody's interior decorating here, just pointing out some options. In terms of our personal and household products, again, not always easy to find out what's in them. There may be other apps than this. This is the one which I have found and used. Giki has got lots of different applications in terms of sustainability, but one of the ones I find very useful is they have an indication of what products are in some of our household products and can give you an indication which ones are safer than others. Next thing we can do is actually get some ventilation, as we've discussed already. If we can replace that contaminated air with fresh air, then that's going to be a big benefit to us. So things to think about. When cooking, you might think the extractor fan's only there for when things get burnt or smelly. Really, if you're going to switch on a gas combustion for your cooker, then just get that extractor fan on straight away. And also, when we have things which are creating a lot of moisture, like showers, or if you're cleaning your kitchen with sprays, again, get extractor fans on if you've got them available. Now, in the warm just now, it maybe doesn't seem too difficult to keep the window open a little bit to allow air to move through most of the time. However, sometimes it can be just uncomfortable. It might be too cold, or maybe even a day like today, too hot to have the window open. So if the problem is it's too cold, then maybe we can ventilate the building while it's unoccupied. Or alternatively, wait until the warmest part of the day, wrap up everything warm, and just open as many windows as possible, make sure there's no blockages between them. You can do that for a few minutes for every day just to get some real good throughput of air. If it's a really hot day like today, well, maybe you can leave having the windows open until the evening or the nighttime when it's a bit cooler. But do try to get some airflow through your space to help get rid of some of these indoor pollutants. Another strategy is to use plants. The ones that I'm showing images of now have all some research evidence, and in fact, these particular ones have been researched by NASA. So they've all got some evidence supporting their ability to absorb VOCs. Now, what I'm still trying to pin down is exactly how many you need in a room. But I've started by making sure that everybody in my family has some of these plants. So most of them are just greenery plants, but some of them have flowers like the Gerbera daisy. But there's plenty of options here if, like me, you're a hay fever sufferer and you don't want to be bringing additional pollen into your space. So we've got things like the bamboo palm, ivy, lots of the dracenias, the good old-fashioned spider plant, the peace lily, and another flowering one there, the chrysanthemum. So a quick summary. In terms of the indoor air quality, do what you can to reduce the contaminants in your living space. replace your stale air with fresh, especially when you're cooking or cleaning. Try to reduce the humidity, because if you keep the humidity down, you reduce the issues with mold and damp. And think about using the plants to absorb some VOCs. If anybody's interested in looking at some of the sources I've used, then that's a full list. Now, I know that Kate has been keeping an eye, so if anybody's been asking questions throughout this, she'll be letting me know them now. But equally, if you've got some questions, you haven't had time to jot them down yet, then do please feel free to put them now in the Q&A section.
Okay, thanks very much, Vicky. That was really fascinating. I certainly learnt a lot of new things there, so thank you very much. We've had one question in so far asking about wing walls. Are they ever retrofitted to improve air circulation in a room?
I have no evidence of that ever happening. I think possibly because people don't know an awful lot about wing walls. I think they're really underutilized. I think they have a lot of unrecognized potential. So unfortunately, I haven't heard about it happening. But as I mentioned, I'm thinking about how I can redesign my windows to help that. Unfortunately, I have got fairly large areas of fixed panel in my windows in my house, and that's something I would like to change when I can get around to changing the windows. And I will be keeping that window which can open as I showed, the sort of like 90 degrees straight open, because then I can use that as a wing wall.
Thank you. I don't think we've had any other questions posted, but we've got a couple of minutes, so I'll just put, we've got a new one come in. So in your opinion, sorry, things are jumping around on the screen. What is your opinion on using cheap MP 2.5 detectors?
Yeah, I can actually read that one. So using a Kitera laser eggs to understand the air quality and remind them when to open windows, which is really great. To be honest, Peter, I'm in a similar position. I've made my own little particulate sensors with a PM 5003 attached to a Raspberry Pi. I'm now understanding just quite how unreliable Raspberry Pis can be, that they do flake out at awkward moments. In terms of their accuracy, I know that there's a lot of concern about their absolute accuracy. I bought 4 and I was testing them against each other. They were giving quite replicable results. So I'm happy with them as a trend indicator. And I've had that sort of same input from other people that they're happy to use them as trend indicators. But I think you probably couldn't get it to stand up in court if you wanted to take that kind of detail into a court. But I think, for the kind of use that you're saying, these can help you, remind you to open your windows. I think that's a really great use of them. And I think the cheap PM 2.5 detectors are really good for that kind of use.
Thanks, Vicky. So we've had another interesting question come in as well about how do you think the COVID-19 will affect energy efficiency regulations in terms of air tightness and ventilation? So yeah, another good question.
Sure. I kind of thought there might be some COVID questions coming up here. So here's a slide I prepared earlier. Actually, I have to say this is not my research. This is from Dr. Clive Shrubsole at UCL, who's done a lot of investigation into this area. And I think he's produced a really nice graph here, which helps understand it. So yes, a lot of the regulation and advice that's coming up now about COVID is basically significantly increase your air throughput, reduce recirculation, and that also applies to heat pickup. If you've got a heat pickup system where you're trying to pick up the heat from the outgoing air with the ingoing air, some people have expressed concerns that there could be some sneak through from there if they're not entirely airtight. So by losing some of these things which helped us with energy efficiency in the past, I think it is likely that we're going to get some increase in energy use. As Dr. Shrubsole pointed out, as we increase the amount of ventilation, we do tend to lose more of the heat energy from the building. So that's particularly important when we're getting into the autumn and winter. There is also a sweet spot, as he's pointed out. It's about trying to find that sweet spot between getting sufficient ventilation to remove your indoor pollutants without pulling in too much of the outdoor pollutants. And that's going to vary a bit depending on your outdoor air quality. So I don't think anybody's got a real number to put onto that, but that there is a concern that we do need to balance that.
Thank you. And another question come in talking about, can green architecture fight against COVID-19?
Okay, there's lots of implications in that statement about the green architecture. There's, to me, a really good environmental building in a suitable climate will have really good natural ventilation, and that's been the focus of my discussion today. I don't profess to know a huge amount about mechanical ventilation, although I do know about some things which can help give us some help with the natural ventilation, like transpired solar collectors and things like that. That's part of my research. Solar preheat on air, that's part of the transpired solar collector concept. So we can use solar energy to preheat air to get that fresh air into our building. We can have good natural ventilation, which if we get good natural ventilation, or actually just generally good ventilation, is what's been spoken about to try and reduce our chances of catching COVID from other people in an indoor space. Recently, I heard that the odds of catching COVID in an indoor space was 19 times higher than an outdoor space. And it's all about the virus particulates being in the air. So the general consensus is if we can have good ventilation, then we can reduce our issues in that respect about catching illness.
Okay, great, thank you. And so in terms of the adjustments that should be made in real estate, in terms of ventilation in real estate or commercial buildings, presumably that's a lot of the things you were talking about in your presentation today.
Yeah, particularly if people want to look at some particular resources, I've put a few here. CIBSE, that's the Chartered Institute for Building Service Engineers, have got good advice. There's also, if people are thinking about actual ventilation in relation to sort of mechanical ventilation, filtration becomes really important. People tend to be quite aware of what a HEPA filter is. And just in this slide that I'm showing, the high efficiency here refers to the efficiency of removing the particles, not to energy efficiency. So high efficiency filtration, the HEPA, what they're saying is they can get about 99.7% of the airborne particles down to 0.3 microns stopped. So that's why it's widely used in hospitals. And you'll also maybe see it in sort of like high quality vacuum cleaners, particularly if you've got an asthmatic in the house, like I have, then I'm always looking for one that's got good HEPA filtration. The other filters tend to be reported in relation to MERV, that's maximum efficient reporting value. So anything below 13 is not considered at all suitable for trying to stop the virus particles because they tend to be on quite small particles. I've heard that above 13 has some effect. So you can see here that MERV 13 to 16 have got about 75% efficient removal of those really small particles. So they're starting to work in the right direction. An important thing to consider is that anybody who's swapping out or cleaning those filters is going to have to take a lot of precautions, because the whole point about those filters is they are trapping the COVID contaminated particles. And the COVID is known to have a lifetime on many surfaces, and I haven't seen it fully documented on lots of surfaces. I know things like, for instance, copper, it's got a very short lifetime. Cloth actually has quite a short lifetime. But some of these figures are also based on previous knowledge from SARS and maybe not necessarily from COVID. So there was, again, and I do apologise for the quality of this particular image. That is the quality I picked up from the source. I wasn't able to find a better version. Again, you can see about this in terms of air change. So you can see something like measles, which even with high air change, it is quite infectious. But when you see something like SARS, and this is about SARS, not necessarily about COVID, you can see that it actually responds really well to high ventilation rate. And because of the similarities between SARS and COVID, there's an understanding that that could also apply to COVID. So just in case you're having problems working it out there, SARS is the second one from the bottom, the kind of purpley colour.
Okay, I think we've got one more question, Vicky, if that's all right.
Sure.
Somebody asking, is it possible to be in a sort of fully air-conditioned bay shopping centre during the COVID pandemic?
Okay, again, there's a lot of variables in there. Given all the concerns about COVID just now, I would hope that everybody is being ultra careful about their air conditioning, making sure that there's really good quality filters and that they're being treated appropriately. But how would you know? And equally, no matter how good the air conditioning is, if somebody happens to have the virus and sneezes within a couple of meters for you, you're in their zone. Air movement's also very important. If you happen to just be in the air train, so if somebody has the virus a meter or so away, and it happens to be, maybe you're not even facing them, but the air is moving in your direction. Something that might be of interest to people here is actually the impact of masks in helping us prevent the spread of COVID. If you follow the link that I've got there, that link actually shows a video of somebody exhaling, sneezing, and it shows the difference between that happening with and without the mask. So it really shows the huge benefits that the mask has in preventing the virus particulates spreading out from the person, so really reducing the possibility of any exchange. So in the question about the air-conditioned mall, like everybody else, I'm having to go and get my food shopping, so I'm walking into places. I'm just being careful in the way that I think is sensible. I'm wearing disposable gloves. I'm wearing a mask. Partly that's because I've got hay fever and I don't want anybody panicking if I happen to sneeze when I'm in a few meters of people. And I think if we're all careful about that, it'll help us significantly reduce the chance of transfer. But I have to say, I'm not a virologist, so that's you have to take that, and the government's getting great advice from amazing scientists and virologists. I'm not one of them. I'm just giving some common sense advice based on what I've been picking up.
That's great. Thank you very much, Vicky. Right, I think we're going to have to leave it there today, but we've had some really interesting questions, and thank you so much everyone for joining us today, and thank you to you, Vicky, as well. It's been most interesting. So if anyone has any further questions or would like to get in touch, then feel free to contact us. Otherwise, we're going to sign off the session for today. Thanks very much. Bye-bye.
Thanks, Kate, for organising, and thanks everybody for joining in.
Pleasure.
Bye.
Bye-bye.